now know how to find the largest eigenvalue and the corresponding eigenvector of a matrix numerically using power method. For most problems of physical interest where eigenvalue and eigenvectors are important, the maximum eigenvalue and the corresponding eigenvector are usually sufficient. However, in some cases, we also want to know the other eigenvalues and their corresponding eigenvectors. In those cases, we may use what we will see now is the inverse power method. The idea is very simple. We start with the same problem AV equals lambda V, and then we show that A minus Qi inverse V equals lambda minus Q to the power minus 1 V, which means that if for a matrix A the eigenvalue is lambda and eigenvector is V, for a matrix A minus Qi inverse the eigenvector is the same V, but eigenvalue has changed to lambda minus Q to the power minus 1. Now we'll see now that with proper choice of Q, we can find all other eigenvalues and eigenvectors of A. Recall the standard eigenvalue problem AV equals lambda V, and we know that this is equivalent to A minus lambda IV equals 0. We know that eigenvalues come from the root of the polynomial P lambda, which is determinant of A minus lambda I. Setting it to be 0, we can find the values of lambda if we want to find it analytically. And then we have learned using simple techniques, we can use power method to calculate the dominant eigenvalue and the corresponding eigenvector of the matrix A. Now we are ready to see the inverse power method. Here also we start from the same system AV equals lambda V, and then if I now write A minus Qi V, that will give me AV minus Qi V. Instead of AV, I can write lambda V because I know AV equals lambda V. Here, Q is a number which we try to take it such that Q is different than all the eigenvalues. It's not easy to know the eigenvalues beforehand, but if we have some idea where the eigenvalues we will learn, the entire process becomes much easier. And if Q becomes equal to lambda, then we have a serious problem that you will see quickly. Now that I have A minus Qi V equals lambda minus Q of V, I can multiply both sides by A minus Qi inverse multiplied by lambda minus Q to the power minus 1, and then I'll get this relation A minus Qi inverse V equals lambda minus Q to the power minus 1 V, and then this lambda minus Q to the power minus 1 we can write it as mu. So mu equals 1 by lambda minus Q. So you can see that we have set up an eigenvalue problem of A minus Qi inverse. If for matrix A the eigenvalue is lambda, corresponding eigenvector is V, we see that for A minus Qi inverse the eigenvalue is mu, which is lambda minus Q to the power minus 1. Eigenvector is same V, which you can see here we have same eigenvectors. For a particular case, we may be interested when Q equals 0. That brings us to A inverse. For A inverse, the eigenvalue of A inverse is mu, that is lambda to the power minus 1. The eigenvector is same V. So the matrix A and A inverse, they share the same eigenvector, and the eigenvalue of A, if it is lambda, then for A inverse it is lambda to the power minus 1. Now let us say that we are interested to find the smallest eigenvalue of A. We know how to find the largest eigenvalue using power method, but now we are interested to find the smallest one. For the minimum lambda, we know that mu will be maximum if I take this mu as an eigenvalue of A inverse, which means that when I am trying to find out the minimum of lambda of the matrix A, the problem is same as finding the dominant eigenvalue of A inverse. Since it is a problem of finding dominant eigenvalue, we can simply use power method over A inverse to find this mu max, and as soon as I get mu max, 1 by mu max will give me lambda min. That means I'll get the smallest eigenvalue of A. The largest eigenvalue of A, of course, we can directly apply power method over A. For the smallest eigenvalue, I have to apply power method over A inverse. So the largest and smallest are now taken care of. We want to see how to figure out the other eigenvalues of A. We have to select now Q judiciously. So we select Q in a way that this lambda j minus Q is less than lambda I minus Q, where I is not equal to j. What does that mean? It means that I select Q in such a way that it is close to lambda j, it is much closer to lambda j than any other eigenvalue. So this means that lambda j minus Q to the power minus 1 will be greater than lambda I minus Q to the power minus 1, and this is very important. So for the matrix A minus Qi inverse, if I select the Q in such a way that Q is very close to lambda j, then Q minus lambda j is very small. That means lambda j minus Q to the power minus 1 is very large, and in fact this mu j, which is lambda j minus Q to the power minus 1, will be the dominant eigenvalue of A minus Qi minus 1. Now, because this is the dominant eigenvalue we are talking about, we can use once again the power method to find this mu j, since mu j is dominant eigenvalue. Once we know mu j, it's very easy to find the corresponding lambda j, which means I have to select Q close to lambda j, and then I use power method and I find lambda j just like this. Similarly, selecting Q closer to other eigenvalues, I can one by one find all the eigenvalues of matrix A. Let us now summarize the process. We know we are solving the problem AV equals lambda V, that is our eigenvalue problem, and we know that using power iteration we find the maximum lambda and the corresponding V. Please note that when we talk about maximum, minimum, etc., we are talking only about the absolute values. So then the maximum lambda and corresponding V we are getting directly from power iteration. Then we start with A minus Qi inverse, and then judiciously selecting Q, we will get one after another lambda and the corresponding V. Wherever we select Q, the closest eigenvalue to Q, I'll get it. And this technique is something we call inverse power iteration with shift. Here this Q is called the shift parameter, and this is called inverse power iteration because we are having power iteration over this inverse of a matrix, and it has certain tricks that we'll see quickly. This is not on any matrix, it is inverse of certain matrix. Now we understand this. The key to this technique is the proper choice of the shift parameter Q to get the eigenvalue, eigenvector. One of the problem is of course proper choice of Q and nothing we can do about it. But then there are other problems. Let us say that I do have proper choice of Q, but then I have to figure out A minus Qi inverse if I want to apply power method over it. And this is not always easy, especially if the matrix is large. Finding it inverse is very time consuming, and we usually avoid that sort of possibilities. So what do you do then? What we do is that the repeated matrix multiplication, which is the key of power method, when we bring it over the inverse matrix, what we do is that we transform it as a repeated solution of linear equation. This is the key of using inverse power method. So let's see what it is. So let us say we want to find the minimum eigenvalue of the same matrix A that we have dealt before, 7 3 6 4, and we also did an exact solution. We know that the minimum eigenvalue is 1 and the corresponding eigenvector is 0.447 minus 0.894. This is a very simple case, but it will give us the idea of how to use inverse power method. We want to do power iteration with A inverse to find out lambda minimum. And we know that the power iteration, the normal procedure is I find V at k plus 1th iteration as A inverse multiplied by V of kth iteration, and then I take the normalized V at k plus 1th iteration as A inverse Vk divided by norm of A inverse Vk, and I continue this process till convergence. Now the key to go through this process without directly finding the inverse is that to get Vk plus 1 as Vk1 equals A inverse Vk, I write is as A Vk plus 1 equals Vk, and then you can see that this is a linear system now where Vk plus 1 is our unknown. So I know A, I know Vk plus 1 in our unknown. So I can solve this linear system for Vk plus 1 using maybe Gaussian elimination or LU decomposition or any other linear solver. It could be iterative solver also. Using them, I can find Vk plus 1. Now I don't have to get the A inverse explicitly, rather I solve this equation. Now the idea is that this is the equation I have to solve every iteration. I have to solve it once until convergence. Every iteration I have to solve it. So for instance, if I start with an initial guess of a matrix 1 0 as my eigenvector, then to find out V1 I have to solve A V1 equals V0, and then I have to use probably Gaussian elimination or something else to find out V1 from this. And then I can keep on repeating this process until I hit the convergence criteria. As I told before, for most engineering application, of course, the largest eigenvalue will be sufficient, but when it is not, then this is a standard procedure which we can use. For your exercise, you go through this entire process with this matrix 7 3 3 4, and you find the eigenvalues and eigenvectors. That means it will have two eigenvalues and two eigenvectors. You find both of them using power method and inverse power method. Of course, you do not compute A inverse explicitly, rather you use the technique I just explained. That's all for this lecture. Thank you, and I'll see you in next class.